which is nice. By the time the temperature is of order 1 MeV, all antibaryons have annihilated away. So pretty much we kind of got rid of the antibaryons, and we get eta baryon, the ratio of N baryon over N gamma to be 5.5 times 10 to the negative 10. Thus, there are many fewer baryons than relativistic particles when the temperature is around an MeV. So basically, that's another way of saying that the Big Bang made a lot more of these, or right after the Big Bang, we had a lot more of the relativistic particles, such as the photons, electrons, positrons, mass, and the neutrinos that decouple from them, and way fewer baryons. This will also affect certain things that we will look at going forward. And of course, these baryons were pretty much mostly just hydrogen, because hydrogen, remember, is just the one proton. At this point, we're not really considering the elements as neutral atoms, neutral elements, or anything like that, because it's too hot and excited to be a neutral atom. So really, when we say elements, we just mean the nuclei. If the nucleus is that of a hydrogen nucleus, then we say it's hydrogen. So basically, again, in the Big Bang nucleosynthesis environment, way fewer baryons than there were the photons, positrons, and electrons, and we call it still the radiation-dominated universe. So one task, or our task in this section, will be to determine how the baryons end up. Were the system to remain in equilibrium throughout, the final state would be dictated solely by energetics, and all baryons would relax to the nuclear state with the lowest energy per baryon, which is iron. Stephen, hello. However, nuclear reactions which scale as the second or higher power of the density are too slow to keep the system in equilibrium as the temperature drops. So in principle, we need to solve the equivalent of a Boltzmann equation that we have mentioned, not really mentioned, but it's there for all the nuclei. That is a set of coupled differential equations. In practice, at least for a qualitative understanding of the result, we can make use of two simplifications that obviate the need to solve the full set of differential equations. The first simplification is that essentially no elements heavier than helium are produced at appreciable levels. So, oh, thank you. I'm enjoying studying because I heard that Donald Trump is banning TikTok and astronomy. I don't think astronomy can be banned. Steven says, hey all friends. Hi Steven. Thank you, Ella. Hi Doro. Hi Batman. So this is basically saying that this is Baji. Thank you. That's Baji. Thank you. Thank you for being here, Ella. Don't leave us. Be in the live. Welcome, welcome. So, one thing that actually simplifies matters for us for the Big Bang nucleosynthesis is the fact that we did not have very much elements other than hydrogen. Even helium we had pretty small amounts of. So it's not like we have to do a lot of math with a lot of different types of things when it came to the baryons. The photons, electrons, positrons we already covered. The neutrinos we already covered. And as you know, photons are bosons. We have Bose-Einstein for that, for the distributions if we need to. Positrons, electrons, and neutrinos, these are fermions. We have Fermi-Dirac for that. So pretty much the only thing left at that point is the baryons. And, you know, for what it's worth, fortunately, unfortunately, there weren't many. So it's not like we have to consider a lot of complication in the Big Bang nucleosynthesis when it comes to baryons. So don't be afraid. We will cover it really quickly here today, okay? Big Bang, greatest event in the universe's history. We would not be here. I have to go to bed. Ella, good night. Baji's here.